Hi, everyone. Welcome to Decoupling Streaming Pipelines at Scale. So why decoupling? First of all, my colleagues always tell me that I love this word too much. And second, our experience in Coralogix has shown that decoupling was one of the main ingredients that allowed us to scale our streaming pipelines. And this is what I would like to talk about today. Okay, so my name is Harel. Great to meet you. Before we talk about what we've done, I would like to provide some context about our company so we can understand Coralogix's relationship to the world of data pipelines and why real-time streaming has become a native part of who we are. We are essentially an observability data platform. However, contrary to the standard market perception, we believe that data analysis should happen in real time and not only after being indexed or stored in some database. Two main reasons, actually. The first one is our customers' expectation to identify and alert on issues as soon as they occur on their systems, which is, of course, a natural expectation when it comes to observability systems. The second one is their expectation that the price will be reasonable. Reasonable means not only cheap, but also a price that takes into account that not all the data has the same importance from the customer's perspective. Any reliance on storage creates an inherent scalability problem. The scale is effectively bounded by the storage capabilities and the system becomes very, very inefficient. As a company that already serves thousands of customers today and aspires to have millions of customers in the future, this is a limitation that we wanted to eliminate. And this was the reason why we chose to go towards real-time streaming. Okay, so let's see what we're going to talk about today. We'll start by discussing why we chose to go with streaming. We'll talk a bit about state management, which is the main challenge when working in a streaming fashion. We'll talk a bit about the classic model of working with streaming and what problems we encountered when working with this model. We'll talk about KafkaStreams and its state management capabilities. And we'll show the model that we're building our data pipelines with in Coralogix and discuss how it allowed us to overcome these state management challenges. So why didn't we go with the batch processing? Several reasons. The first is that the artificial cutoff that's applied as part of batch processing causes a lot of complex issues that don't seem like issues at first, such as late data handling and how this cutoff affects the business value. Another reason is that batch processes requires a large amount of resources over a relatively short time span. And this leads to very complex resource management and eventually to a lot of waste and over provisioning. By the way, even cloud providers themselves are starting to struggle with this issue because this pattern of resource usage limits their ability to predict the customer's resource requirements sufficiently. Also, batch processing time is directly affected by any rise in traffic. When combined with the previous 2 points, this could lead to batch processes not being able to keep up, causing very costly redesigns and manual maintenance effort. Also, the nature of batch processing leads to very complex observability issues, since most observability platforms are not planned for low-rate sparse data that is very much characteristic of batch processing. And the last point is that batch jobs they have a relatively low natural resolution, hours or minutes, and can be unsuitable for cases where the needed resolution is higher, such as, for example, in our case. These complexities, along with the way that we perceive our business model, have led us to actually go with stream processing as a first-class citizen. Okay, so we've decided to go with streaming, but naturally this came with a set of challenges. In general, there are two types of operations that can be done on data: stateless operations and stateful ones. Stateful operations are naturally much more challenging since they bring up a lot of questions. Where should the state be stored? How to handle data which arrives in the wrong order, and how to handle late data. And also how to join data from the other data sources. When talking about distributed systems, state management even becomes much more challenging since it brings to the table another set of questions. The first is how to shard the state and how to make this sharding efficient relative to the sharding of the traffic. And the second question is how to handle state recovery after deployments and crashes. One thing is definite in any distributed system, pods and machines will always go up and down, which means that we cannot rely on memory state only. In summary, state is a fault tolerance liability, and in distributed systems, faults are, of course, the natural part of normal behavior. By the way, with batch processing, this liability is easier to manage, and this is one of the reasons that historically a lot of data systems were implemented with batch concept rather than streaming concepts. Okay, so before we go into solutions, let's have a quick recap on the main features of Kafka itself, and the ones which help to manage distributed state. The first topic is topic partitioning. In Kafka, a topic is not stored as one big unit, but is split into a set of partitions. The data consumers divide the work on the partitions between them. Each customer is responsible for reading from a subset of those partitions. The second thing is message keys. Each message that is stored in a topic has a key, and Kafka knows how to perform a process called compaction, which knows how to delete old messages which belong to the same key and leave only the last one. We can look at these compacted topics as topics that effectively hold breadcrumbs of state over time. Reading an entire topic from start to end can be used to construct a view of the full states that's stored in that topic. Similar to many other companies, we have started with the classic model, which today we call a Streamolith. The idea is a service that consumes data from a Kafka topic, performs some processing, and sends the results to another Kafka topic. And during processing, the service communicates with external databases that effectively hold the state that is needed for the computation. An almost natural part of this model is actually adding local caches to the service in order to optimize the access to the external databases. This type of solution brought a lot of issues with it. Some of them almost entirely eliminated the value that we wanted to get from streaming in the first place. Let's go over the main issues that we've encountered. First of all, the stream performance depended on the external database, causing unpredictable and long latencies in the high percentiles. The stream's availability depended on the availability of the external database. So when the database went down, the stream was impacted and eventually even stopped working. The database performance was directly dependent on the stream as well. Scaling the stream caused a significant impact on the database, and also led to very large startup times of new stream processes. The stream scale was effectively bounded by the scale of the database. Every time we needed to scale the stream, we had to account for it in the scale of the database itself. And last but not least, we had to match the sharding model of the stream to the sharding model and key model of the database, which was very complex and led to a lot of maintenance effort, slowing the evolution of our system essentially. When looking at all these issues, we can see that this model essentially prevented us from taking advantage of the benefits of using streaming, and frankly, it also cost us a lot of money. Okay, so we've realized that when using this model, what we've realized when using this model was that a lot of the issues that I mentioned are related to mixing between the actual processing, which is CPU or memory bound, and accesses to the external database, which are network bound by nature, and effectively contain a dependency on some external system. And usually this subject is discussed in the context of differences in latency, which is obviously very relevant here as well. But I would like to emphasize the differences in the context of reliability and predictability. We can see in the table 3 types of computations: internal ones, ones that involve accessing some local disk, and ones which involve another system and are essentially network bound. The more we go down from one computation to the next, we can see that not only the latency grows, but also the chances of external failure. Computations which are CPU or memory bound are much more reliable and less exposed to external failures than computations which only involve disk access. When accessing another system through the network, the chances of failure rise even further. Any dependency on an external system exposes our computations to a complete set of resources which we don't have any control over, and naturally this makes those computations much less reliable. One of the main conclusions from our experience was that making our streaming topologies CPU bound makes them much healthier and much more scalable. By the way, this difference in reliability can be observed in the evolution of client libraries. Code which accesses the network is designed in a way that allows catching and recovering from errors, while code which performs internal computations or accesses the disk usually does not contain any error recovery logic. This reflects the fact that network access to other systems is highly unreliable and requires much more attention by developers. Okay, so let's summarize what we would like from a healthy streaming system. We would like fast and efficient scaling and recovery. We would like to decouple the scale of the stream from the scale of the external databases. We need the ability to launch processes without any bad impact on the database. We would like fast and predictable processing even for higher percentiles. We'd like to be, with the stream, to be actually immune to temporary infrastructure failures. We'd like the stream to be CPU bound. And obviously, we'd like to have natural and easy monitoring and debugging capabilities. The way we chose to achieve this is by decoupling the stream state from external dependencies as much as possible. We'll soon see how we achieve that, but before that, let's talk a bit about the choice of KafkaStreams itself. We saw earlier that the classic use of Kafka just for input and output of a stream does not provide the answers to what we need, but why did we choose KafkaStreams? First of all, it's a standard JVM library which comes with a natural set of advantages. We can use the entire JVM ecosystem. We can easily leverage our own internal systems for deployment, monitoring, debugging, etc. And there's no need to learn an additional technology or manage the resources of some external cluster. Second point is that KafkaStreams is only dependent on Kafka itself, which we are already using for a lot of other use cases in the company, and it's a major part of our infrastructure. Also, KafkaStreams is very opinionated in terms of how streaming is done, which helps a lot for learning and for propagating the knowledge throughout the company and among developers. And the last thing and the most important one in our context today is that KafkaStreams has inherent support for distributed state management, which is actually achieved by combining a set of technologies, as we'll see in a moment. So how does KafkaStreams allow managing state? The state itself is available to the stream as a key value map that's called a state store. Every change in the state is written automatically to some change of topic, which is a topic that KafkaStreams manages by itself. The topic is, of course, a compacted one containing the so-called breadcrumbs of the entire state. Behind the scenes, KafkaStream manages this map through an embedded RocksDB instance. RocksDB automatically manages the state in both internal memory and on disk files. This split between the memory and the disk is used both for recovery, as we'll see in a moment, and also in order to allow holding a state which is larger than the available physical memory. Kafka itself is responsible for managing the sharding of the main traffic topic, as in any other standard Kafka-based service. And KafkaStreams itself knows how to manage the store sharding in a way that matches the sharding of the main traffic topic, so access to the store will be efficient. Let's see how these capabilities are being used in practice. When a container is restarted, KafkaStreams recovers the state by using the data in the local disk and then using the changelog in order to complete any leftovers that were not written to disk. What happens when a pod goes down? Due to our use of Kubernetes stateful sets, the disk of the old pod is reattached automatically to the pod replacing it, and then the state is recovered in the same manner as a container restart. During scale up or down, there's obviously no data on the disk, so the entire state is recovered by reading it from the beginning of the changelog topic. The reading from the topic is optimized so that only partitions that moved will need to be consumed by the process. In all these cases, we can see that there's no external database that's being strained, apart, of course, from Kafka's network, which is what Kafka brokers are optimized for. In fact, this combination completely decouples the external databases from the stream itself. Okay, so to leverage these capabilities of KafkaStreams, we needed to decouple the Streamolith, and we did it according to the model that I will show now. The idea of this model is to use these capabilities of KafkaStreams in order to move all network-bound parts of the topology, except for Kafka itself, of course. Let's define each part of the model. When referring to source, we mean that we take every interesting activity in a database and we write it to a message as a message to a topic in Kafka, a so-called source topic. The way to do it is using our own service or some generic product such as Kafka Connect that performs this out of the box. Sync. When referring to a sync, we mean that writes to a database don't happen directly by the service itself. Instead, the service sends a message with the data that needs to be written to the database into a sync topic, and an additional service reads the messages from this topic and handles the actual updates to the database. In this case as well, the sync service can be our own service or a generic product that knows how to do this for a specific database type. It's worth noting here that the semantics of a sync and the source topic are identical, allowing us to use the same topic sometimes as a source and sometimes as a sync. Stream. With Stream, we can see how it all comes together. The source topic is being read by KafkaStreams, and KafkaStreams uses it to fill the store with the relevant state. When the stream needs the data, it accesses the key value map of the store as part of the processing and uses it for the computation. When the stream needs to update something in the database, it doesn't write to it directly, but sends a message to the relevant sync topic. The sync service for that topic reads the message and performs the actual updates to the database. The update of the database will eventually lead to a message in the relevant source topic, and the state will be updated in the store, exposing the changed data to the stream. It's important to note here that this cycle causes an inherent delay between updates and the reflection in the stream. This delay is called eventual consistency and is an inherent part of any distributed system that needs to be taken into account. Local caches, for example, introduce eventual consistency as well. Using KafkaStreams in such a way allowed us to factor in the implications of eventual consistency in a proactive way, which helped us a lot in creating high-quality streams and evolving our system. Okay, so what did we accomplish from all of this? First thing, the stream itself is not dependent anymore on anything external other than Kafka, which, as I've mentioned, is optimized for network access in terms of throughput and robustness. The stream behavior became fully predictable, no latency outliers, and the stream has become fully CPU bound. The cost has also become linear and predictable as well, which made capacity planning much easier and has reduced our maintenance effort considerably. And also the resilience of the external databases grew significantly. scaling and recovery of the stream do not affect the databases directly anymore. Some additional accomplishments. The stream resilience, the resilience of the stream itself became much better. Problems in the database do not propagate directly into the stream anymore. Also, by adding new streams, adding new stream doesn't affect the scale or the performance of other systems, other streams. Before that change, the database was effectively a coupling point between different streams. The behavior of one stream could easily impact other streams which use the same database. In fact, we've reached a situation where stream scaling and deployments have become fully robust. They are fast, no state is ever lost, and there's no direct impact on any of the external databases. Here are some examples which show how our cost and performance improved because of this change. For example, bringing up 300 new nodes for a stream takes now a lot less than 1 minute with zero impact on any of the databases. The move to CPU-bound streams utilizes resources much more efficiently, and this led to an 80% decrease in the stream's cost, and like I mentioned, to much easier capacity planning. One last thing is that from an infrastructure perspective, Kafka, which gets much more load when using this new model, is only in 5th or 6th place in terms of cost. All other infrastructure above it are essentially storage systems. One last thing I would like to touch is the challenges that we had to deal with when moving to this model. The first thing is the challenge of monitoring topic compactions and retention. This is, of course, a natural part for anyone using Kafka, but when working with KafkaStreams, this becomes much more crucial to everyday work. Another challenge is the configuration and monitoring of RocksDB, which is a very important building block of this new model. The defaults don't fit production, and we need to constantly monitor disk accesses, for example, or the cost of data serialization inside RocksDB itself, etc. An additional challenge is understanding and managing the relationship between keys and balancing the load across multiple processes. Key skewing needs to be well understood and dealt with. We handle key skewing with something that we call local global processing. We'll soon publish a blog post that provides more details about how we do this. Yet another challenge, which is not specific to KafkaStreams, was the impact of the number of partitions in a topic on balancing the load across processes. We've solved this by writing our own auto-scaling Kubernetes operator, which knows how to take the number of partitions in each topic into account and perform smart auto-scaling decisions based on it. We are going to open source this operator in the near future. One last thing which I haven't dived into in this talk is the fact that there is a need to write separate services for each source that we are interested in. In a multi-service system with the proper deployment infrastructure, this is not a large effort, but we are working on making it easier for our developers by providing the ability to create such services in a declarative way. Okay, so let's summarize what we've discussed in this talk. We've described why we chose streaming. We talked a bit about the complexity of state management in stream processing. We've shown the classic model that is often used to manage stream state. We've touched a bit about on the abilities of KafkaStreams to manage distributed state. And finally, we've shown how the current model we're working with that decouples all network-bound dependencies from the stream using KafkaStreams capabilities has allowed us to maximize the value that we get from stream processing.